Okay, here's our notes. These notes are going to be about the product rule, but before we get to talking about the product rule, I want to talk about all the other derivatives we have looked at so far and talk about what they look like in the formula packet, okay? Because the formula packet can be a little confusing at times, so I want to kind of draw attention to the formula packet so we can see what these mean and recognize that we know what these are. Okay, so the derivative of x to the n, so if we have f of x is equal to x to the n, this is just our basic rule. This is our basic rule. And so in the formula packet, it tells us, therefore, the derivative is equal to n times x to the n minus 1. So I'm just going to copy that down. So therefore, f of prime of x is equal to, we bring the exponent down in front, so that's where the n comes from, and then we have x to the n minus 1. We subtract 1 from the exponent. So that's our basic derivative. Okay, so that's the one everybody I think is pretty comfortable with. Okay, the next one, here we have the derivative for sine. So f of x is equal to sine of x. So this one we discovered just by using Desmos. We asked Desmos to show us the function, and then we recognized what was going on. Okay, so at this level of mathematics, you are not expected to be able to do a proof or discover that the derivative of sine is cosine. You just need to be able to apply it. And in fact, I don't even know what the proof is. I tried Googling it, tried looking it up, and I didn't find anything readily available, so I said, you know what, we'll just use Desmos. We'll just look at it and figure out what's going on. Okay, so that's what we did in class. But you just need to be able to know that the derivative of sine of x is cosine of x, but do you have to have it memorized? No, it's in the formula packet. Okay, you just need to be able to apply this when we do have a sine function and we need to know how fast it is changing. We know how to take the derivative. We just change it to cosine x. Okay, and then the next one is what if we have a cosine function and we need to know how fast that is changing? Well, that gives us negative sine of x. Again, we use Desmos to discover that one. Okay, the next one in here is the derivative of tangent. We're actually going to prove this one, so I'm not going to write this one down right now. We are going to get back to this one. If you have the function of tangent, we are going to prove that the derivative is 1 over cosine squared. All right, the next one, we also saw this on Desmos, that if you take the function e to the x and you figure out the derivative, it's actually it's itself. It's its own derivative. So that means that for any point on the graph, its rate of change is the same as the value of y at that point on the graph, which is crazy. That doesn't happen with any other functions. And then we had natural log of x. So f of x is equal to natural log. And remember, natural log means that there's a base of e. Its derivative is 1 over x. And again, we discovered these by just using Desmos, just playing around in Desmos. Okay, so that is a way of discovering mathematics, is just noticing things. And so that's a inductive proof rather than a deductive proof. When you notice something happening, you can call it an inductive proof. But we didn't really do a formal proof. All right, so the other things that we wrote down, we already took notes on the chain rule, but I want to point out what's going on here. Okay, so I'm going to write this again. So the chain rule, and then I'm going to sort of annotate it. So the chain rule in the formula packet says y is equal to g of u, and u is equal to f of x. Okay, so what does this mean? Basically, it's y is equal to g of f of x. So we use the chain rule when we have a composite function. Okay, so let's make a note of that. Use the chain rule with composite functions. Oops, ran out of room. So that is a function inside of another function. Function is inside the other function. Okay, so when you do have that, when you have y is equal to g of f of x, Okay, so when we have y is equal to g of f of x, we can call f of x u, and so then we can say that y is equal to g of u. So then when we do our derivative, dy dx, am I running off the bottom here? Oops, sorry. Let me change that angle. Dy dx is going to be equal to, remember, the derivative of u. So the derivative of u, so we take this derivative, okay? So we're going to take the derivative of u. That's my du dx. Okay, so this derivative, take the derivative of this one, goes here, times the derivative of g of u. So you would take the derivative of this one, and that would be dy du. Okay, because here's my y, here's my u. Okay, here's my u, and I'm taking the derivative in respect to x. Here I'm taking the derivative in respect to u. Okay, so we take our composite function and we take the derivative of the inner part and we take the derivative of the part that we changed to u, and then we just multiply them together. Okay, so that's what this is saying. This is the derivative of one of the functions times the derivative of the other. Okay, what's another way of saying that? If I had another way, but this is the formula that's in the packet, so that's why I did that. But another way of saying that is if I had h of x is equal to g of f of x, then derivative of h of x is going to be equal to the derivative of g times the derivative of f. Actually, let's shorten that. Sorry, you probably already copied it down. So the derivative of h is equal to the derivative of g times the derivative of f. Okay? So there's that. So this is what we have in the formula packet. So it's just, if you have a composite function, it's the derivative of one of them, the inner one, times the derivative of the sort of the outside function. Okay, product rule. On to the product rule. So for the product rule, that is when you have, say, f of x is equal to g of x times h of x. So they're not nested inside of each other. They're actually two functions that are being multiplied together. When you have two functions that are being multiplied together, you have to take the derivative of each of them and then do that cross-multiplying and adding them together. Okay, so let's see, how do they write it in here? Okay, so in the formula packet, they change it to y equals u times v. Okay, so I'm going to change f of x to y. That's my y. And then I'm going to change g of x. I'm going to call that function u. And h of x, I'm going to call that function v. So if we're doing this notation, I'm going to go ahead and do this notation right here. And then the other notation, I'll do it over here. These mean the same thing. So this is two ways of writing it. The product of two functions. Okay, so there's a couple ways of writing it. So if I'm writing it like they did in the formula packet with u and v, what I need to do is I need to take the derivative of u. So I would take let's see, what am I doing? Taking the derivative of u, so that would be du dx, and then I would take the derivative of v, so that would be dv dx, and then you have your original functions. Actually, you know what? Oh, God, I hate that. I should have started by separating these. Okay, first we have to identify our two functions. I am so sorry. I hope you didn't do that with pen. Okay, u and v, let's write it underneath it. So here's the original function, u, and then I would do du dx, take its derivative. Here's the second function, and I would take its derivative, dv dx, that's its derivative. Okay, so these are the functions, so these are the derivatives. Okay, then I would multiply these together, and I would multiply these together. So I'm going to have u, so my final function, dy dx, is equal to u times the derivative of the second function, plus the second function times the derivative of the first function. And that's what you see in the formula packet. That's what they have here. Okay, if we write it with f of x, then again, I separate these. This is what I did in class today. I separated these out. I then took the derivative and the derivative, and then I cross-multiplied those. Okay, so I did g of x. I'm going to run out of room here, so let's put a big giant arrow down. I'm going to put it down here. Okay, so I would have g of x times the derivative of the second function plus the second function times the derivative of the first function. And that would be the derivative of the whole thing. Okay, so this is the way that the formula is written in our formula packet. This is the product rule in our formula packet. Here it is using f of x, g of x, and h of x. But it's the same idea. It's the first function times the derivative of the second function plus the second function times the derivative of the first function. Now, does the order matter? No, I could have written this part first and this part second, okay? Because u times v is the same as v times u. I could have swapped those, okay? So let's go ahead and put one example into our notes. So I'm going to get a fresh page so I have plenty of room. So here's an example, because examples are usually easier to follow than the formulas, but I do want you to realize that this is the formula in the notebook. So the derivative of the function that's made up of, a composite function, not a composite function, sorry, the product of two functions, u and v, okay? So I have a function that is composed by multiplying two functions together. You take the derivative of both of them and then multiply the derivative of the second one times the first function, and then the derivative of the first function times the second function, and add them together. That's the product rule. All right, where was I? Let's do an example. Okay, so example, if y is equal to x times x squared plus 2x, okay, we already should notice right away that it would be way easier to just multiply this out and not use the product rule. Okay, this would be way easier to just not use the product rule. But I'm doing an easy example with the product rule because it's easier than doing a hard example with the product rule. Okay, so anyway, here we go. So I am going to say, okay, y is equal to u times v. So what's u? U is going to be equal to x. And v is going to be equal to x squared plus 2x. Right? So then I'm going to take the derivative of u, so du dx. The derivative of this is just 1. And then I'm going to take the derivative of v, so dv dx is going to be 2x plus 2, just using my basic derivative rules. Now I'm going to do my crisscross applesauce. And so I'm going to have dy dx, the derivative to the whole darn thing, is equal to the first function times the derivative of the second one, plus the second function times the derivative of the first function, times 1. And then I can simplify it and combine like terms. So dy dx is equal to 2x squared plus 2x, and then this one, when I distribute the 1, I'm just left with x squared plus 2x, and then combine like terms, I get 3x squared plus 4x. And there it is using the product rule. Okay, so the product rule is really better used when you have crazy things with like sine and cosine and natural log, things that you can't just easily simplify, because this would have been way easier to have just distributed and then used your basic derivative rules on this one. Okay, so make sure you're using the appropriate rule unless you're required to use a particular rule. Okay, so in this case, I showed it with the product rule, but this one really would have been easier to just have distributed that x and then taken the derivative using basic derivatives. Okay, I think that's it. That's the notes. Bye-bye. See you Monday.